Hello everyone, welcome to this lecture series on foundation engineering. This is part 4 of lecture 1 on foundations on expansive soils. I am Amit R Chauhan, head of civil engineering department, Lakshmi Institute of Technology, Sarigam. Welcome you all. In the first part, we have discussed regarding the introduction on expansive soil. Then we have discussed on the various mechanisms which are involved in the swelling behavior of the black cotton soil. Then in the further lecture we have discussed regarding the identification of expansive soil and which are the different tests which can be conducted in case of expansive soil. In this class we are going to discuss regarding treatment of expansive soil and various kind of foundations which can be made in case of expansive soil. Let us see first the effects of swelling on structures. The most obvious way in which the expansive soil can damage foundation is by uplift. That is because of expansive nature, the soil will try to generate uplift pressure, and which is going to disturb the structure condition. The most obvious way in which the expansive soil can damage foundation is by uplift. As they swell with moisture increase, the swelling soil lift up and back lightly loaded structures, continuous strip footing, and frequently cause distress in the floor slab. So basically these are the different parts of the structure which can be affected by the expansive nature of the soil. First one is the lightly loaded structure which are not having that much amount of vertical pressure acting on the soil. Second one is continuous strip footing. As strip footing is at the periphery of the building or any kind of structure, they are easily susceptible to the variation in the moisture change. And last one is frequently cause distress in floor slab. As floor slab is in direct contact with the soil, it is more susceptible to the moisture variation. Because of the different building loads on different portion of the structure's foundation, the resultant uplift will vary in different areas. Based on the contact area of the soil variation around the structure will be different. That is, at the edges it will be different, at the center it is going to be different, and at the periphery of the building the amount of moisture will be different. And based on the availability of moisture content, there will be different expansion of the soil, which can result into differential settlement of a building. Now let us see the effect of swelling on ground slab. In figure 1 we can see uniformly loaded rectangular slab, the vertical pressure which is acting on the rectangular slab. In figure 2 we can see slab lift up at the corners because there is less confinement. The moisture variation will be more at the periphery of the ground slab. In figure 3 we can see as the vertical load increases, the amount of swell and movement decreases, and on the curve we can see the maximum amount of swelling and movement of soil is at the corner of the slab, then it is at the edge of the slab, and it is least at the center of the slab. As the center of the slab experience the least amount of moisture variation, there will be very less differential settlement and there will be very less expansion of the soil. The loss of skin friction on bridge pier. Bridge piers are basically acting on the property of skin friction. Skin friction is the friction which is generated between the surrounding soil and the pier material. And because of this expansive nature of the soil, the amount of skin friction keep on decreasing because of this expansive nature, and which create the negative skin friction which is acting in the upward direction. In figure 1 we can see this thing very easily. At the beginning of the rainy season, the pink kind of arrows which is going upward is the upward uplift pressure which is generated by the expansive nature of the soil and which is decreasing the resistance of the building. And at the outside area there is continuous rainfall because of rainy season, and there is moisture change in the soil conditions. In figure 2, after 5 to 10 large storms, we can see the expanded soil at the surrounding. And in the figure 3 we can see in the dry season the surrounding soil, because of dry season, it is the water is desiccated from the surrounding soil and it is shrinking, and because of this shrinkage of the soil there will be differential settlement of the surrounding building or the surrounding piers. In this figure we can see, because of uplift pressure which is generated by the expansive nature of the soil, there are cracks in the interior wall because of uplift pressure. This is basically the diagonal cracks which is very severe in nature in the outside wall. Now let us see which are the different treatment which can be done on the expansive soil. First one is replacing the expansive soil under the foundation. The first solution is, if we can remove the surrounding soil around any structure, we can decrease the amount of expansion around a structure. Second one is changing the nature of the expansive soil, changing the property of the soil by mixing with some kind of cementitious material or supplementary material. Third one is strengthening the structure to withstand heave, constructing the structure that are flexible enough to withstand the differential soil heave without much failure, or constructing isolated deep foundations below the depth of the active zone. Active zone is basically is the depth up to which there is more amount of moisture variation and there will be frequently change of shrinkage and swelling of the soil. Let us see first one, the replacing the expansive soil. The first and very simple method is to remove the entire layer of expansive soil up to the firm and non-expansive stratum. That is, wherever we are going to construct any kind of footing or foundation, from the surrounding we can remove all the expansive soil and we can fill that soil with some kind of other material or some kind of other soil which is not that much expansive in nature. Second one is changing the nature of expansive soil. By these kind of means we can change the nature of the expansive soil. First one is compaction, second one is pre-wetting, third one is installation of moisture barrier, and fourth one is stabilization of soil. Now let us see what is compaction of expansive soil. The heave, that is the uplift pressure generated because of swelling of the soil, can be minimized by compacting to a lower unit weight on the high side of the optimum moisture content, possibly 3 to 4% above the optimum moisture. That is, the expansive soil is compacted to a moisture content which is 3 to 4% more than the optimum moisture content which is required for the maximum dry density, so that whatever kind of expansion the soil can experience will experience because of more amount of water in it. Second one is pre-wetting. Wetting this soil before construction so that most of the heave can be formed before construction. This is very good. Before construction, if we wet the soil where we are going to construct the structure, it will try to swell, and if it is swelled before construction, there will be no very much amount of swelling in the soil when we start the construction process. This technique may be time consuming because seepage of water through highly plastic clay is slow. As we have discussed in the last lecture that the plasticity index of the soil is very much more, and the water will go deep inside very slowly, and the swelling nature of the soil will not happen in 1 or 2 days. It needs 15 to 20 days, and because of that there can be delay in the construction of the project. So after ponding, 4 to 5% of hydrated lime may be added to the top layer of the soil to make it less plastic and more workable. So basically 4 to 5% of hydrated lime is added to change the property of the soil. Next one is installation of moisture barriers. The long-term effect of the differential heave can be reduced by controlling the moisture variation in the soil. That is, after constructing the structure, what kind of arrangement we can do to restrict the amount of water entering the surrounding of the building. This is achieved by providing vertical moisture barrier. We can construct some kind of moisture barrier, vertical moisture barrier, below the floor slab around the perimeter. These moisture barriers can be constructed in trenches, that is, we can dig trenches around the periphery of the building filled with gravels. We can fill gravels, lean concrete or impervious membrane. In this figure we can see a protective coating which is provided at the periphery of the structure. In this figure we can see the different means which are used to keep the moisture away from the periphery of the building. At the top they have provided a pitched roof in which shedding is provided so that water goes away from the periphery of the building. Deflection eaves provided past exterior wall to deflect the rain. Gutter conveyance system is provided to keep the moisture away from the structure. Side grading. Side grading means a proper slope is provided at the periphery of this structure so that water goes away from the building, and the underground drainage is provided so that water table don't stay below the structure for longer period of time. So such kind of moisture protection we can use in case of any kind of structures where the amount of expansive soil is more. Next one is chemical stabilization of soil. Chemical stabilization with the aid of lime and cement. We can use either cement or we can use lime for the stabilization of soil. Lime or cement and water are mixed with the top layer of the soil and compacted. After adding soil, lime plus water, we can compact the soil. The addition of lime or cement will decrease the liquid limit, the plasticity index and the swell characteristics of the soil. Means if we add cement or any kind of supplementary unit or cementitious material in the expansive soil, we can decrease the amount of swelling nature of the soil. This can be done up to a depth of 1 to 1.5 meter. As doing to more than 2 meters or 3 meters, it can cost you more as we have to buy the cementitious material. It can be more costly for the overall cost of this structure. Hydrated high calcium lime and dolomite lime are basically used for the lime stabilization of the soil. Pressure injection of the lime slurry or lime fly ash slurry. Stabilizing by adding lime slurry usually to a depth of 4 to 5 meter and occasionally deeper to cover the active zone. Such kind of things can also be done to decrease the expansive nature of the soil. Under-reamed piles. Under-reamed piles are basically such kind of piles in which under-reamed bulbs are provided at the intermediate point in case of pile foundation, which we can see in the figure A at the left side, that at the bottom we have provided a single bulb, then 2 bulbs and then 3 bulbs. And at the right side we can see under-reamer, which is normally used to form the bulb below the soil. Now let us see what kind of arrangement we can do so that we can form foundation in case of black cotton soil. First one is granular filling. In this method, excavation is carried out to a depth greater than the depth of the foundation by about 20 to 30 centimeter as shown in the next slide. Means filling a granular filling more than 20 to 30 centimeter than the original depth required for the footing. Freely draining soil material such as a mixture of sand and gravel is filled and compacted up to the bottom level of the foundation. That is, the footing or the foundation will not stay in direct contact with the expansive soil and it will be direct contact with the granular filling. We can also use reinforced concrete footing is constructed at this level over which the brick wall may be raised. Means we can make such kind of vertical moisture barrier also. In the figure A we can see that only a simple sand filling is used around the footing, and in the figure B filling of alternate layer of sand and marum is used, and in figure 3 or C marum and ballast rammed into the soil with sand filling is used, and in the figure D they have used sand filling and concrete block at the bottom of the footing. So such kind of granular fillings with different kind of arrangement can be used to support the foundation in case of expansive soil. CNS technology. One of the methods for constructing embankments on expansive soil is to lay a CNS layer. Now what is CNS layer? CNS layer is basically a non-swelling clay layer at the base of the embankment to isolate the subsoil from the moisture, mainly rainwater, coming in vertically downward direction. That is, your foundation is dusted on a CNS layer and then expansive soil is there, so that the footing will be not in direct contact with the expansive soil. For any clay to be classified as non-swelling clay, it should not have swell pressure more than the specified value. The value is 0.5 kg per meter square. The larger the thickness of CNS introduced over the expansive soil, the lesser would be the resulting swelling and deformations. Now let us see what is drilled piers. Built piers the same characteristics as skin friction piers, except that they depend only on end bearing. The bottom of the pier is built out by under-reaming to a diameter 2 to 3 times larger than the pier shaft. That is, in case of drilled pier, a bottom drilled bulb is provided to support the expansive nature of the blackwater soil in order to provide additional bearing area on the bearing stratum. This system is most commonly used in areas where competent shale or limestone is uneconomically deep. Means if the bearing stratum is at the very deep, then where the footing is provided, then in that conditions drilled pier can be provided. We can see easily in this figure. In the figure A, basically they have shown L1. L1 is the unstable zone. Unstable zone is that zone in which the variation of moisture will be more, and because of that variation there will be shrinking and swelling property of the soil will be more. And QUP is the uplift pressure which is generated in the upward direction, which is acting against the resistance provided by the vertical action of the building. And QR, which is the stable zone, is the bearing capacity acting as a resistance toward the uplift pressure. And in case of figure B, it is shown that the footing or the pier is provided with a bulb at the bottom. So because of that, there will be increase in the resistance, which is indicated by QR2, and the length will be LB. Now let us see what is the conclusion of all the four parts which we have discussed in this series. First one is expansive soil are very problematic during the construction of foundation, that we all know because of its swelling and shrinking nature when it is exposed to water. Foundation on expansive soil is affected by the behavior of soil under different moisture condition. Based on the amount of water variation, the expansive soil will change its nature, and because of its change in nature, the foundation will experience different kind of load variation. The swelling tendency of expansive soil on foundations can be quantified by the swell potential and swelling pressure parameters. Basically, these are the parameters which are very important to identify the expansive soil. First one is our swell potential, and second one is the swelling pressure. The major engineering problem of expansive soil on foundation is shrink swelling characteristics of the soil. It is possible to build successfully and safely on expansive soil if the stable moisture content can be maintained, or if the building can be insulated from any soil volume change that might occur. The procedure for such success is as follows. Means if we are restricting the moisture entry inside the boundary of the building, or if we are using any kind of vertical moisture barriers, or if we are restricting the change in the moisture content of the expansive soil, we can safeguard our structure. Testing to identify type of clay mineral present and problems associated with it. That is, we should, before constructing any kind of structure on expansive soil, we should find out the amount of clay minerals present in it. The minerals like kaolinite, illite or montmorillonite. If there is more amount of montmorillonite present in the soil, we should first do ground improvement techniques, and then only we should make any kind of structure on it. Designed to minimize the moisture content changes, we should design in such kind of way that the amount of moisture variation will be very less and insulate from soil volume changes. Built in a way that will not change the moisture condition of the soil and maintain a constant moisture environment around the building surrounding. Thank you.